Alright, starting with number 12. That's big enough. Traveling west with the speed of this, collides head-on with the minivan traveling east with the speed of this. They stick together. Ooh, as soon as I hear stick together, I think, how do I describe the collision? Totally inelastic. And move with the constant velocity of this to the east after the collision. What is the mass of the minivan? All right. So, non-energy bar graphs for this one. Y momentum before and after. So, 12, and I might even put in here the collision is totally inelastic. Two objects become one object. Right? Just to remind myself, just to let the person who's evaluating me know I understand what they mean by stick together. Okay. So now I need to do my before. So what do we have? Is it a truck in a minivan? Is it a car? Car in a minivan. So we have our car. And our minivan. So beforehand, the car has momentum. The minivan is just parked, isn't it? Head on the van traveling east. And okay, so car is traveling west. Minivan is traveling east. I know my handwriting isn't like the best, but where do you see a W? Or would you like to borrow my glasses? Oh, you're sitting upside down. That's an M.
The car's going west.
Yep. This way is west. This way is south. This way is north. This way is east.
Why?
This way is south. Because we're in Australia. I didn't feel like switching my drawing around. They're arbitrary, aren't they? So during they're in contact, and I've got the impulse on the minivan caused by the car would be in that direction. The impulse on the car by the minivan would be in that direction. And then afterward, I have one object to the east. Mary, you make fun of my drawing, you have to do it. Momentum, our car minivan.
You could also write momentum total, right?
Huh?
You could also write momentum total.
You could write momentum total. Yep. So that's what I would expect in your diagrams. Right? And what's nice is directly from my before and after diagrams come my solution. So I might do things like, right, momentum, from my equation sheet, momentum is the inertia times the velocity. Right? Which way are we going to call positive? Towards the east or towards the west? East is positive? Okay. All right. So momentum of the system, this is also from our equation sheet, right? We pull up our equation sheet. These are right down here. There's our conservation of the system. And I think, oh, momentum's back in unit 1. Oh. It's like a review. So that's from our equation sheet, the momentum before of the system equals the momentum after of the system. And we're using that little prime mark to indicate after. So beforehand, I had positive, well, I had the momentum of the car as a vector plus the momentum of the minivan as a vector equals the momentum of this new car minivan creation that's a vector. Right? Add up all the momentums before, they equal all the momentums after. Now, the car we said was moving in a positive direction. That'd be plus. But the minivan was moving in a negative direction, so I put negative in there. And then positive, the car and the minivan after, because it told me it was moving east.
Wouldn't the minivan be positive and the car be negative since the minivan is moving east?
Is the minivan moving east?
Yeah. Car traveling west.
West, you're right. Right. Good catch. Very good catch. So the car should be negative and the minivan should be positive. But then the car and minivan I got right? Good. And inertia of the car, speed of the car, plus inertia of the minivan, speed of the minivan equals inertia of the car minivan combination, speed of the car minivan. So I could also, rather than, this is the mass of the car plus the mass of the minivan, right? The two of them combined to make that new body. So now it's just plugging in, right? 1,200 kilogram car. There you go. Guys, make sure you're using your time wisely, right? 12 meters per second. Plus m, we don't know. 9.4 equals 1,200 kilograms plus mm. 1.5. And just solve for mm. Or MW, whichever one. I'd either factor things out or maybe throw it into a solver. Like Wolfram, if I didn't feel like doing any algebra. So I could understand. I know. I think, if I did my algebra in my head correctly, oh, did you get this one correct? Okay, you may want to pull out the paper and a pen or anything. Yep, so we're going to do number 8. Which, if you look at the answers, you think, oh, I need to do energy here. Really what you need to do is momentum And what the problem is trying to point out to you is that because if kinetic energy is conserved, it's an elastic collision. Is this an elastic collision?
No.
No, it's inelastic. Therefore, they want you to find out really kind of how much kinetic energy is lost. Because you have the initial, which I'm expecting to be very high, and then the final, which I'm expecting to be lower. Because some of that energy that was kinetic went into squishing the bodies. So I might mention that here in my Y about KE not conserved goes to smush. Momentum is conserved. All right, so the problem is trying to emphasize to you the difference between those two in this type of collision. Make sure I got this right. Always. There's nothing we can do to not conserve momentum as long as you're looking at the whole system.
You're saying that B should equal A.
No, I'm saying B should not equal A. Remember, because I said that the momentum was conserved, but not the kinetic energy.
So that energy is converted
Heat, sound, yeah. So it doesn't stay as kinetic energy. Now, if they were to hit a spring and then expand back, if that spring was really efficient, it might go to potential and come back out as kinetic, and it could be an elastic collision. That's kind of how those magnetic fields that we use to get them in the lab did it. But here, it's not. It's the energy is not staying as energy of motion. Yeah. Okay, so I was looking to see the original cart the second cart was stationary. That's what I wanted to see. So we've got these carts on an air track. Remember, if you can't draw as well as me, don't worry about it. Do something.
Even it's just like boxes on a document.
Yeah. Momentum 1. Like that. Wow, my track got really hilly really fast. Right. I'm going to call this cart 1 and this cart 2. So, impulse of 2 caused by 1. Impulse on 1 caused by 2. And then they stick together, right? Yep. Oh, good. They're back on the flat. Which way, if these two carts stick together and become one mega cart, which way do you think it's going to move? To the right.
Whatever direction it was moving.
And I'm going to call that momentum 1, 2. Because that's my new name for my cart, my mega cart 1, 2. Not 12. 1, 2. No. That's how I know if you're not a fan of the mega cart, you don't know how to say its name. Comma would let pretenders get in there. The mega cart. Momentum equals inertia times velocity. Kinetic energy equals 1/2 m speed squared. Alright, so momentum of cart 1 equals the momentum of mega cart 1, 2. Right? Oh, these should all be vectors. Sorry about that. mass 1. Oh, fuck, too many parentheses. Inertia 1, velocity or speed 1 equals, this is m1 and m2 together for megacart. Velocity or speed of 1/5. Right? Now it's plugging in 0.12.
We're not doing card 2 on all of them.
Correct. So right away I know what's its momentum. 0. So I could write that, but you guys are smart, you know that. Identical cart. Ooh, I'm going to predict that the speed is going to cut in half because the inertia just doubled and the momentum stayed the same. Gay mental math. Did I get it right out? That part? Now, they don't ask me what the speed is or the velocity is even. They ask me what the kinetic energy is before. Well, before, we have two objects, right? So the kinetic energy total before would be the kinetic energy of cart 1 plus the kinetic energy of cart 2 beforehand. And that I just figured that out, right? 1/2 m1 v1 squared. What's the kinetic energy of cart 2?
0 because it isn't moving.
0 because it's not moving. And then just plug in.
Why do you use 0.12 twice?
I was finding the moments like that. The mega cart.
The mega cart. Afterwards, I only have one object, so there's just the kinetic energy of the mega cart 1/2, known as 1/2. Who's that person? That would be 1/2 the mass of 1/2, which is 0.24 kilograms, 0.225 meters per second squared. And then you can just put it in your calculator and try it. And my guess is it will work. Should work. Left. All right. So we have another inelastic collision, which is good. If you go and look at like a couple of the ones from C Block, you have an elastic collision and such, which we haven't done any in this class, but go and look at their videos so you pick up on it. And I'll send out a PDF of the work also. So we got this train moving, it collides, it's inelastic. I'm going to talk fast so we can get through this one. Equal mass. Equal mass. And then moving in the same direction at this. And they want to know the speed of the connected carts and how much does the kinetic energy of the system decrease during the collision. So kind of like what we did, the second part is definitely what we did, but just that further answer of the first one minus the second one, right? And change. Alright? So, I'm going to skip the writing because you guys know what to write. Beforehand, we have a train, and we have a train. We'll make it look differently. So it's a double-decker. Train car, connected to a train car. Okay, so they're supposed to be identical. That's okay. So we'll call that momentum of 1, and this momentum of 2. They hit. have our equal and opposite impulses. Move off as one big happy train car, mega car,
Or Megatrain.
or mega train. I don't know, Megatrain has a good kind of Saturday morning bad movie vibe. Megatrain, attacked by Megatron.
Megatrain comes out to theaters.
Yeah. So yeah, you'd look up that, right? Right? They're all moving in the same direction. They all have the same mass, so I'm just going to say m v1 plus m v2 equals 2m v1 2. Because when they join together, they have twice the mass, right? Each one brings m to it. And now let's plug in some numbers. 2,500? 100 or 1,000? 1,000. Kilograms moving at 2.5. Am I right, Alex? I heard him, Captain. Yeah? Good? Oh yeah, because 25,000 cancels out of each one. 1.5, 2.5 plus 1 is 3.5. 3.5 divided by 2 is 1.75. And now, kinetic energy before equals KE1 plus KE2. Kinetic energy after, skipping letters on you guys. Kinetic energy after is just going to be KE of Megatrain 1, 2. Changing KE equals KE after minus KE before. 1/2 2m v1 2 squared minus 1/2 m v1 squared plus 1/2 m v2 squared. Fortunately, you can't cancel anything out. You can factor things if you really wanted to. But, and then you know everything in here. What was this? 1.75. Right, I forgot it back here. .5.
Is that a 0.25 in your first word?
Huh?
Five.
Yes, that's what that's what I had from the, yep. Close enough.
I need to redo my math, because I got some.